Okay, we're almost all here. uh, while we're waiting to start, are there any questions, concerns, issues? So everybody's good. Excellent. Actually, I have a question. Was my reviewing random variables? Again, we just did a little bit of it. Is that something you want me to keep doing? Is that helpful? It's helpful. Okay, we got one helpful, two helpfuls. Okay, so I'll keep doing it. And okay, and that material is basically FYI. So you're not explicitly responsible for it, but hopefully in covering that material, this whole random stuff will start to become a little clearer. It is kind of confusing. And actually studies have shown that people are actually quite bad at probability. They're bad at estimating risk. They will typically be way off in terms of what they believe the probability of certain things happening is. But that's something that models, particularly the kind of stochastic models that we're looking at here, can at least help alleviate to a certain extent. Okay, so let us begin. We are continuing looking at what random variables, I'm still back on that, what these event graphs are about. And we're going to spend a lot of time on them, because even though actually after today you will have received most of the methodology, I've covered at least most of the methodology, kind of learning how to work with them, learning how to use it as a tool for building simulation models is something that needs some experience and working with actual situations. Okay. So today, the topics are, well, canceling edges, parameters on edges. Those are the two methodological topics. And then going to give a couple of examples, a couple of simple examples that are useful as little building blocks for being able to do certain tasks when a model is called for it. And then we're going to look at a model of inventory which uses this parameters on edges concept. Okay, so here we go. Okay, first the canceling edge. Okay, what this is about is in the normal execution of a discrete event simulation, what we've seen so far is once we've scheduled an event, the only way to get it off the event list is for it to bubble to the top and have it be executed by the event list, and the event list is what removes it. However, there are certain situations where we actually want to remove an event before it occurs. So why do we have event scheduling remorse, as it were? Well, sometimes it's when an event is scheduled, there's every intent of having it occur, but then other events occur which cause that event to become somewhat moot. So the idea of a canceling edge is it kind of looks like a scheduling edge, with the exception that it is a dotted or a dashed arrow instead of a solid arrow. The second, oops. The second difference is that there's no time delay. So for a scheduling edge, it has everything. The only thing it has is the Boolean condition. And the rule is that when as a modeler, you've decided that a certain event is going to cause other events that had been previously scheduled to be canceled, then it's denoted this way. So what this kind of canonical representation says is that when event A occurs, then if this Boolean condition is true, then the first occurrence, the earliest scheduled occurrence of a previously scheduled event B is removed from the event list. In other words, the event B is canceled, but only when this particular event occurs. I mean, here's kind of a little thought experiment to see how this might be useful. Supposing event B is an event that's the impact of a missile. So some sequence of events has scheduled the launch of a missile, which in turn has scheduled that the missile is going to impact. And that's, say, event B. But then in the model, there are also countermeasures. And the countermeasures ultimately result in another event. Let's call it A. And if in the model something like this were to be denoted, the Boolean condition would be if the countermeasure was successful. And if the countermeasure is successful, then that means that impact event that had previously been scheduled is not going to occur. The missile is going to be destroyed. And so if you don't do anything, that impact event is still going to be on the event list. And so the model, you may think that it's been canceled, that it's not going to happen, but it's going to happen unless you do something about it. In other words, if the event is canceled, then again, if A is intercept, the condition is intercept successful, and then B is the impact event is canceled. That's just one example. Here's another example, is that you've been hopefully working on your arrival process. Again, very simple event graph model, but carries a lot of how should I, like any hello world or simple first model, it carries a lot of it takes a bit of stuff to get it working, or maybe a little bit of stuff, who knows. Anyway, supposing we wanted to stop the arrivals after a certain amount of time. See, here's the thing. Because, as you've seen in the computer assignment, typically these inter-arrival times are randomly generated. If we wanted to stop, let's say, at time 1,000, we don't know how many arrivals are going to happen by time 1,000. And if we run the model again with a different random sequence, then we're going to get a different number. So here's how that could occur, is that we have a time, we'll call it T sub S, and it's going to schedule an event, say stop or stop arrivals. And when that event occurs, what it's going to do is it's going to remove the next scheduled arrival event. Now, here's the thing, is that if you've been looking at what happens in the arrival process, at any given time, there's only one arrival event on the event list. And that's what schedules the next one. So if you don't do anything, it'll just continue forever. In the example, or in the lab last Thursday, I showed that, well, we can tell the event list, which is called schedule in SimKit, we can tell the event list to just stop at a particular time. So we don't necessarily need this entire mechanism if all we're doing is the arrival process. But what we might want to do is, if we're modeling, let's say, the day in a particular facility, what we might want to do is say open at a certain time in the morning, say, run for a certain amount of time, let's say for 12 hours. And then at the end of 12 hours, we want to kind of shut things down. But if we do the stop at time as we were doing, that kills everything. That ends the entire simulation. If what we want to do is we want to simply stop the arrivals but keep the processing going, then this is how we could do that. Okay, so just for if all we're doing is the arrival process, this isn't totally necessary, but just as a little way of stopping certain parts of the simulation while allowing others to continue, when we don't know when that's going to happen. I mean, we know when it's going to happen, but we don't know, in this case, how many arrivals there are. Okay, so that's an example of a canceling edge. As we continue, we're going to see a little more, an example where the canceling edge is a little bit more essential to how the model works. Okay, the second addition to our methodology, and as far as events go, this is actually the final one, and that has to do with parameters on edges. So if you have noticed that the analogy between events and how they're implemented is that each event is represented as a method in SimKit. Now, if you carry that analogy a little bit further, you know that methods can have arguments. And how do we invoke a method with arguments? Well, we invoke it by passing a parameter, and that parameter is some expression, just like we're invoking a method. So something similar can be done in using event graphs. So this is the canonical representation of it. And what this means is that when event A occurs, then when the Boolean condition I is true, again, the Boolean condition and the time are always part of it. So if the condition is true, then event B is scheduled to take place with a delay of t. And when B occurs, so you notice that B has an argument, I'm just calling K here. This J that's in the box on the edge is the parameter that's passed to that event. And what happens with that is that when the event occurs, the value of its argument is the value that this expression was when it was scheduled. So you can think of it as kind of like a time capsule. In other words, the typical use of this, or a use of it, is to kind of save some quality, some state, some aspect of state at one time and pass it to the future. In other words, we want some future event to know something about what our state was when it was scheduled. But you see, when this event occurs, when event B occurs, that will, in this case, be some time later. And if we were to evaluate this expression at this time, it would have a different value, or typically it might have a different value. So what we do in this is we kind of, unlike invoking a method in a program, in which case it happens immediately, here it's kind of delayed. Again, think of it like a time capsule. So a time capsule, J, and J is, even though it's a letter, it could be some expression, and we'll see. We're going to see an example where it is an expression in a very simple case. And again, as with the regular case, if the Boolean condition is not specified, it's defaulted to be true. If the time delay is not specified, it's defaulted to be 0. So if neither one of those are specified, then we have a 0 delay, and it's always true. Okay, so here's an example of how we can apply this. So here's a case where, for whatever reason, we want to have an event that's going to occur in m times. When I think in a model we'll look at either tomorrow or the day after, we'll see where this little structure can be useful in initializing state variables that are arrays. So again, we're kind of stuck with this zero-based indexing. It can throw you off, as it kind of did to me yesterday for the umpteenth time. But anyway, so here's how to implement a for loop in using events. So again, run is always where we start. So what this would do is this is going to put run on the event list at time 0. And what it's going to do is it's going to schedule this event. I'm calling it init because that's actually the name that we're going to be using for initializing state variables. But right now we're just focusing on kind of how this works. All right. So run schedules the init event. Don't know why this keeps doing this to me. Okay, with a delay of 0. And then when init occurs, okay, the first init is going to occur and the value is going to be 0. The Boolean condition here is that I is less than m minus 1. So we want to do this m times. And what init is going to do is it's going to schedule another init. So if I is less than m minus 1, it's going to schedule another init, but it's going to pass I plus 1 to that event. And when that event occurs, so the second time it occurs, it will be 1. And the third time it'll be 2, etc. Okay, so what I want to do is I want to kind of show you this in action. So let's see. Let's see if I can everybody see this?
We just see your PowerPoint, sir.
Just the PowerPoint. Okay, so I need to stop the share and then reshare. Okay, so here's an implementation of what I just showed you there. So I have a class called for loop. It extends SimEntity base, and that's all of our event graph components in SimKit will extend SimEntity base. And for some reason, this should have been private. Okay, so we have a single parameter, which is going to be the maximum number of times that init is going to occur. As I mentioned before, with the arrival process, we typically have 2 constructors. One, we generally have an empty constructor, and that's for it's for things that we'll talk about later if we get to it. Or we have a master constructor, which will have as an argument all of the parameters. In this case, we have a single parameter. All right, so here, remember that the run event here, which is implemented as the do run method, and it has a wait delay of init. And then here's how you pass an argument. And we'll talk about this, about the mechanics more as time goes on. But the first argument is the name of the event you're scheduling. The second argument is the delay. In this case, the delay is 0. And then the third and fourth and more optional arguments are the parameters that you're passing. So this schedules init with a delay of 0 passing the value 0. So here's the init event, and again, it had an argument. We called it I, just as a generic index. And the Boolean condition was if I is less than max number -1, it will schedule a wait delay, the init event with a delay of 0, passing it I plus 1. So that's what all we did was I just translated what the event graph did. We had a single parameter, again, setters and getters. This is something that, again, we'll talk about a little bit more, but in this particular case, this is only going to work if the maximum number is strictly positive. If we have 0 or a negative number, then that's a bad parameter. And so if we try to pass that, then we want to throw an exception, which is what we're doing here. Now, because this is a small demonstration, I'm going to violate my usual convention, and I'm going to run it from the main method here. So how do you run one of these things? Well, again, we instantiate it. So here I'm going to do 5. So I want the init event to occur 5 times. And again, when we print this out, that will just verify that the parameter 5 got in there. We are running if we run in verbose mode, that will show our event list. And then reset, start simulation. Those are the 2 calls that invoke, that actually initialize. Reset initializes, and start simulation runs the simulation. So if we were to run this, we see the following. Okay, so this was the print line, and we see that the max number got in there. So here's how, remember, we always start with the run event on the event list. So reset, the schedule reset, put the run event on the event list. Then the execution is always the same. You take the next scheduled event, in this case run, and you executed state transition. In this case, there was no state transition, but all it did was schedule the first init. And so here's where that happens. And then notice that in the event listing, it shows what the argument is, the parameter that's been passed. And so when here now init with an argument of 0 has occurred, and is 0 less than 5 minus 1 or 4? The answer is yes. And so it schedules init with 0 plus 1 or 2. And then when the init with 1 occurs, 1 is less than 4, so it schedules 2. When 2 occurs, is 2 less than 4? Yes, so it schedules 3. When 3 occurs, is 3 less than 4? Yes, so it schedules 4. And then when 4 occurs, is 4 less than 4? No. And so notice that nothing gets scheduled, and so the event list is empty. Now, one thing to also notice, you may have been wondering about these little numbers in the square brackets. And what those are as each event occurs, the event list, the schedule class counts, just simply counts them. And we see that there have been 5 init events, which is what we were going after. Okay, so that's how, again, just that's how that works. Let's go back to or where do we go? Okay, so that was an implementation of this event graph. Okay, so here's another example, or here's an example of an application of this, is that we, in this case, we actually might not care about the init event itself, but only be using it as a mechanism, as a means to put a certain number of other events on the event list. So in other words, at time 0, we want to have m instances of this event A on the event list. So how do we do that? Well, again, we kind of take our basic for loop that we have here, only now every time init occurs, it will schedule our event. And so since init occurs m times, then at the beginning of our simulation, or when this is all finished, we will have m instances of the event A on the event list. So that's what we're trying to do. And let me show you how that works. So here's another class. And here I'm actually extending the for loop just because of the programmer virtue of laziness. And again, I'm adding another parameter called delay, because I just want to, the events that I'm going to schedule, I want to delay by just a little bit. So here's how we extend one of these classes.
Or we can't see your screen.
You can't. Okay, well, thank you. I thought I was doing it, but I guess I was not. All right, you see it now?
Yes.
Okay, thanks. All right. Because, yeah, I saw it just fine. I don't know what your problem was. Yeah, maybe by the time this is all over, I will have finally gotten it together with this Zoom stuff. Although I guess some people are concerned about the security on this. So if anyway, okay. So here is the class, which is, again, what are we trying to do? We're trying to schedule a certain number of events on the event list. And I'm going to reuse what I did on the for loop, again, the virtue of laziness. So again, I have a default constructor, or an zero parameter constructor. And then now here, because the superclass has this max number, again, what I call it doesn't really matter at this point, but my first call is going to be to super, passing that value. And this delay is just going to be how long the delay is between the init event and the event I want to schedule. And the event I want to schedule, I'm just going to call it an event. I mean, what it does is not important, but what is important is the fact that I want to run the simulation, and I want, at the end of the simulation, I want there to be m events, m of these n events on the event list. Okay, so we have our additional parameter, which is a double, which is that delay. And again, if that's less than 0, then I want to throw an illegal argument exception because that's not kosher. Okay, so I probably should have named this a smaller one, but okay, I want it to be as descriptive as possible. So here I'm instantiating it and I am giving it 5. I want to create 5 of these, and the delay is just going to be 0.01. And I just want to give a little delay to show that. So again, we'll print this and we'll see that. You notice that for the for loop, we just had this one parameter. When I print this, we'll see that it has both parameters. Now, just in passing, and again, we're going to circle back to this, but another way of stopping an event, stopping the simulation, is in this particular case where I want to stop after exactly this many init events, because I want to stop the simulation and see what the event list it looks like. So this is the other way of ending the simulation. I'm saying it's called stop an event, and it says stop after this many of these events that have this argument. And when I'm specifying what the class of the argument is, I need to use the object wrapper for a number of reasons. Again, reset, start simulation, that's all the same as before. And again, the stop on event thing is just to illustrate what I'm showing. Don't be overly concerned about that now. We're going to circle back to that as the course unfolds. But just to run this, we see that, okay, first of all, notice that the print line printed both of the parameters, both the one in the superclass, max number, and the delay. Again, starting the simulation, always start with the run event on the event list. And you notice that as part of each event as it's being printed, also says which component it came from. Again, we'll see more of that as the course unfolds. Okay, so again, here's the run event. Here's the init event. So we go init 0, init 1, init 2. So here's init 1. Okay, so when run just scheduled the init event, init 0 scheduled the next one and also scheduled the event. Now notice that and the reason I put a little delay in is just to make sure that the init events would all happen before this. So even though, so the init event 1 was scheduled, then when init event 1 occurs, it will schedule another an event. And it will leave this one alone. And this is an important thing that I hope was brought home when I asked you to do the event list business by hand. That is, regardless of the order that an event is scheduled, it's that when it's scheduled that dictates what happens first. So even though this init2 event was scheduled after this an event, it happened first because its scheduled time is 0 and the scheduled time for an event is 0.1. So that's sometime later. So we see init 2, init 3, init 4. Okay, so, and then because that's the 5th occurrence of the init event, and because I said to stop after that many init events with an integer as an argument, then it actually just sort of stops. And we see that there are 1, 2, 3, 4, 5 of these n events on the event list. So in other words, what has happened is that by executing this piece and then having each one of these events schedule another event, we were able to put, in this case, m equal 5 of these on the event list at the beginning. Okay, before I go ahead, are there any questions? See, where did my participants go? There you are. Okay. Let's go ahead. Okay, so applying this to a more an actual model, I'm going to look at this periodic review inventory model. I don't know whether you've seen many of these inventory models in the past, but if you haven't, then you're going to see one now. So this is, again, was a very simple model, is that we're just looking at a single item, and for a variety of reasons, that this inventory, the inventory level of this item is only checked periodically. There are actually reasons to do that. The reasons are a little bit beyond what this class is about. When you kind of look into inventory management and supply chains and things like that, then they get into issues like this. But the rule is that when you check the item, if the level of the inventory falls below a certain amount, we're going to call little s, that we place an order that would bring our inventory level up to a big S if it arrived immediately. However, as is typical, the order only arrives after a certain amount of what's called lead time. In other words, we place the order, it's going to arrive sometime later. And in the meantime, demands for our item keep coming in. So what happens is our, quote, customers arrive at various intervals. And unlike the queuing model, they're not going to queue up. They basically show up and they say, I want this many of these items. And if we have them, then we give them to the customer, and we have that many fewer in our stock. But if we run out, then in this particular case, the customer is going to be willing to have it be back ordered. So back order is like, I go to order something, they say, well, we don't have any, but we'll back order it for you and give it to you when it comes in. Okay, so that's how this works. It doesn't always work that way. I mean, if you're, let's say for whatever reason, I go to a Starbucks and they say, I'm sorry, we're all out of the low-fat, gluten-free caramel macchiato. Well, I'm not going to sit there and wait until they get it in. I'm just going to go to the next Starbucks. Although that's not what I would get, but just, okay. So, but in certain circumstances, it might be the only game in town. And actually with some of the supplies that we've been seeing for personal protection and ventilators and things like that, there's often no choice but to just kind of wait till they come in. Okay, so here's how that works. Let me, I think I'll need a pen here. All right, so what we're looking at here is kind of a graph over time of our inventory levels. And what happens is, so the red is basically our level, including back orders. So let's say we start with this many, and then now this is depicted as a straight line, but typically it'll be kind of wavy because the demands are uniform. So as customers come in, our stock level keeps going down and down and down. Now the reviews are here, and so the time between reviews we're going to call T sub R for review. And so here, at every point in time between the reviews, we're going to check our level. So here, let's have another color. Okay, so here we do our review and we look at our inventory level. Our inventory level is above our little s, our trigger point. And so we don't do anything. But at the next review, now notice here, at this review, we see that we have fallen below our trigger point. And so what we do is we place an order for this amount right here. But the problem is it's not going to come in right away. It's not going to come in until this time. So if we were to call this the lead time, then this is, we place the order, and see this, what this dotted line is that this is kind of our net inventory. In other words, we have stuff that's on order and we're expecting it to come in, but so it's kind of maybe on the books, but we don't physically have it yet. So in the meantime, our customers are keep kind of coming in, and notice over here we've gone below the 0 point. So here we have gone into a back order situation. So here we have a back order situation. But then at this time, our order comes in, and so now we have this much on hand. And so notice that the difference is that the amount that we had on back order is now, we're going to fulfill those. So our amount in stock at the point where our order arrives is actually less than our order up to point. So you see how that works? And then here's another review, and we see we're above that, and here's another review and we're above that, so we don't do anything. And then here's another review, and so we place an order. Now in this case, our lead time takes a bit longer. So again, as before, we sort of have we have this many on the books because we have stuff coming in, but we're not going to get it for a while. And in the meantime, we still go into a back order situation here. Okay. So that's how this works. And so all right, so here's how we would start modeling it. And I can see if I'm going to talk about, if I'm going to advance the random variates, I'm going to have to, okay, well, we'll pick this up tomorrow, but again, this is called a periodic review little s big S model, or sometimes big S little s, or sometimes they use R's or other letters. But here are some of our parameters. So we have the time between demands. So the customers who are going to demand this item are going to come in kind of like an arrival process. But each time they come in, they're going to demand a random amount. So the number of items that each customer demands is going to be some random integer quantity. Now, as part of the model, we also had this lead time. So the lead time was the time between when we placed an order and when we received an order. And again, as we saw, it's possible that those are going to be different. So we're going to model that as a sequence or a random sequence. We had another parameter, the time between our reviews. And I'm going to model that as a scalar because that's typically a constant, like maybe every Monday morning we're going to review this. In addition, we have our initial inventory. This is how many we start with. And then finally, these are basically decision variables. The order up to amount, that is how much we're going to order up to when we place an order, and then our little s, the trigger quantity. So now in terms of our state variables, we're going to have a big I, which is the amount on hand, and that's initially going to be our initial value inventory. A state variable B, this is going to be the amount that's back ordered at any point in time. T, I'm going to call the total amount on order. So if we have more than one order that we've placed, then that gets added there. N is going to be the total number of items that we've ordered over time. And NO is going to be the total number of orders. And the thing to note about this is that the relationship between the amount of inventory on hand and the amount on back order is that one of those is going to be zero. In other words, we will never be in a situation where we have inventory but also back orders. And likewise, we will never be in a situation where we have back orders that's positive and also inventory. So one of these is always going to be zero, as it turns out. Okay, so I want to, I'm going to end it here and pick this up tomorrow. Let's sort of keep the annotations there. And then I want to move on to if there are no questions, I wanted to just move the ball down the road a little bit for what we were talking about yesterday about discrete random variables. Again, just to review, that a discrete random variable is characterized by a probability mass function, which is the probability that the random variable is equal to any given value for all of the values in the range. And we saw some examples of this. So this is actually called a Bernoulli with where we have just one or 0 or 1. Rolling a fair die, we have equal probabilities for any one of the 6. Rolling 2 dice and adding them. And then this is an example of actually a binomial random variable. So if we want to count the number of heads, in this case in 3 flips, then it turns out that the range is 0, 1, 2, or 3, and then these are the probabilities. This is the probability mass function. So, and we went through that yesterday. So I have time to just do 1 or 2 more. So let's look at this one. This is what we're, in this experiment, we are counting the number of flips until we get a head. And we're assuming that the probability of heads is P, so it may not be a fair coin. And it turns out the mass function for that is P, that probability, times 1 minus P to the x minus 1. And that's true for values x1, 2, 3, 4, etc. So why does that work? Well, if we get a heads right away, then x is 1, and that occurs with probability P. X is 2 only if we get a tail first and then a head, and that occurs with probability 1 minus P times P. If 3, then see, we have 2 tails followed by a head, and that's 1 minus P squared times P. And then just in general, the only way to have us any value n or x is if there are x minus 1 tails in a row followed by a single head. And hence we have this expression. And notice that there's no upper limit on the possible values. That is, the range of x are all positive integers. So it's discrete, but countable. So a discrete random variable need not be finite. It could be countable. So now here's the thing: the probability mass function has these properties. First of all, it's always between 0 and 1. It can never be less than 0 or greater than 1. And the sum of all possible values is of the mass function is equal to 1. And we can flip that on its head and say that any function p of x that satisfied these conditions is a probability mass function for some random variable x. So just as an exercise, verify that these properties hold for the probability mass functions that we've looked at before. In other words, we've presented a number of different probability mass functions. Verify that, well, it's usually immediately obvious that this first condition between 0 and 1 is satisfied, but verify that they sum to 1. That is always the case. And how should I say? It's like I claimed that they were probability mass functions, and if they were, they would sum to 1. But since you probably have realized by now you shouldn't necessarily take everything I say without checking it out. I encourage you to check that out. Okay, that's what today's was about. Okay, I assume everybody has been able to successfully get their GitLab going. I think there's only 1 or 2 that I haven't seen yet. If you have created your GitLab for MV3302, make sure that you've added me as a developer on it. So if you haven't, then go do that. If you haven't created yours yet, then make sure you create it and add me as a developer. If you have any difficulty or challenge with doing that, then send me an email and I'll try to arrange a person-to-person chat so we can get that all settled. Because as with the other class, the using GitLab is the way that the computer assignments are going to be submitted. So if you don't get GitLab going, then it's going to be very difficult for me to see what you've done. So just make sure that that's happening. And if there are no questions, I will see you tomorrow.